the session this evening, and we'll be sharing that with you afterwards when we're all done. So the way that this will work, we do have a timing for this event for this evening. So we have about an hour plus of content that we'd like to run through. We do obviously encourage you, please, to ask questions if you want to raise your hand as we're going along. We can obviously unmute you, or you can unmute yourself and ask your question. Or if you prefer, you can just type your question into the chat box at the bottom, and we'll either answer that on the fly, or if we run out of time, we'll answer that later. So all being well, we'll be presenting till around 7 o'clock, maybe a little bit longer. And then if there are any questions at the end, we'll open that up to everyone to join in and discuss. So I think without any further ado, I should introduce our presenters. Here they are. So we've got Szilard leading the charge this evening, a solution architect with TigerGraph, and Richard as a wingman and in support, also a solution architect with TigerGraph. So this is the team for this evening. So without further ado, I'll hand over to Szilard, and I'll watch out for people raising their hands if there's questions along the way. Thank you.
Thank you very much, Deb, and thank you very much for everyone to join this. Thank you very much, everyone, for joining this evening with us. So let me introduce briefly myself. As Deb said, my name is Szilard Bárényi. I'm a solution architect at the TigerGraph London office. I have joined TigerGraph late last year, but I was working with Graph beforehand, and I studied Graph theory at the university, and I have spent the last 2 decades working with data, big and not so big, in data storage, processing, and analytics. Before I actually proceed to the topics of this evening, I would like to mention that as you probably guessed, we have to change from on-prem to online due to coronavirus. And I would like to therefore highlight an article that one of our colleagues have posted on our website detailing how the graph technology, the graph database and graph analytics could be used to analyzing the connection between people, or the way they traveled, or in any other innovative way to fight coronavirus. In fact, TigerGraph offers free access to TigerGraph products for researchers and doctors trying to fight the coronavirus pandemic. Have a look at this article. It's very interesting to show how even in case of crisis, graph analytics could be a very helpful tool. But coming back to the main topics, I would like to talk about 2 things today. One is the system architecture of the TigerGraph analytical platform, and the other is the new features of TigerGraph 3.0, which will be released soon. So let's get started with the system architecture. I will provide you first a conceptual overview. Then I will talk about the components, how these are used to ingest data and process queries, and then high availability storage and ACID compliance will close this part. Let's have a look at, let's head over, I don't know how it's called, 10-mile look at the system. On the conceptual level, TigerGraph is a high-performance distributed computing platform which supports real-time data feeding. It runs on standard commodity-grade Linux servers. So far, so good. This platform includes the Graph Store and the Graph Storage Engine, Processing Engine, the REST++ interface, GSQL service, the Graph Studio, and some third-party components such as Apache Kafka and Zookeepers. I will describe these in details on the next slides, but first, let's have a look at it at an abstract level, where TigerGraph consists of 4 stacks. The core stack manages the graph data and performs graph-based computation. The ETL stack loads external data sources to TigerGraph system from local files and files in S3 buckets, and from Kafka and Spark. We have services to ingest data from various sources. The operation stack manages and monitors the system and provides the user interface for applications. And finally, the query and computation stack allows users to develop, deploy, and run the Tiger Graph applications. On a closer look, looking from a different angle, from ecosystem integration point of view, Tiger Graph as an analytics platform plays a familiar role. It ingests data from various data sources, it stores, processes, and analyzes data, and it provides the results to the downstream consumer system. So on the left side, you can see the data sources. The platform includes a flexible high-performance data loader, which can stream in tabular or semi-structured data as part of its ETL stack. On the other side, the REST API is provided to integrate Tiger Graph's existing enterprise data infrastructure and workflow. As expected from a contemporary analytical platform, Tiger Graph is available on premises, in the cloud, and as a hybrid deployment. Let's have a closer look at the components. Let's start at the bottom of the technology stack. There are three components here: the dictionary, which is a metadata storage for the graph and the system, where the information about the vertices and the edges and other details of the architecture or the system is stored here. Then there is GPE, the graph processing engine, and GSE, the graph storage engine. This will be talked about in details a bit later. These services, Dictionary, GPE, and GSE, use two Apache open source products, Zookeeper and Kafka. The Zookeeper is the backend of the dictionary, and the Kafka queuing service is used for data updates. You will see in details a bit later how data ingestion actually works. Let's now jump to the top of this technology stack. We provide various tools and interfaces for people and applications to interact with the Graph platform. The easiest to use is our Graph Studio, which is a web-based UI frontend, and I will demonstrate it a little bit later as part of the version 3 new features presentation. There is also a command line client called GSQL, and there are additional command line tools, mainly gAdmin, which is used to manipulate, start, stop, and operate the services. The Graph Studio and the GSQL client communicates with REST PP, the REST++ interface, which is a RESTful interface. It accepts all kinds of requests from the intermediary components, and it sends these requests to the graph processing or the graph storage engine and fetches information from the dictionary. So this is the main entry point to the Graph analytical platform. And if you are using Graph Studio or Graph GSQL client, then there are actually three additional components in the picture. The Graph Studio and the GSQL client first connects to a Nginx web server, which acts as a proxy for all type of requests. And there are two applications behind this web server: the Graph Studio backend and the GSQL server. The Graph Studio backend, the GSQL server, gAdmin, and actually every other external applications communicates with the database and the Graph platform through the REST API interface via standard REST API endpoints. When you use the gAdmin tool to start a database or check the status, you will see that it lists on the left side. You can see list all of the status of the components, and let's go through in this order as they started up or checked for status. So as I mentioned, Zookeeper is used as a backend of the dictionary, and Kafka provides the queue services for data updates and other communication with the GPE and GSE. The Graph Storage Engine it's not really a storage engine in the sense it's not responsible for storing the data. It is actually responsible for bidirectionally mapping external vertex IDs and internal vertex IDs. I will have a slide on this mapping just after this. I will explain it in a bit. The dictionary, as I mentioned, this stores the metadata for the graphs and the system. There is a component which I won't talk too much about it because it's internet. It's called TS3. It is responsible for monitoring the system health, diagnosing system issues, and collects application statistics. It's mostly interested for the operation team. There is a component listed here, number 6, graph, which is not really a component, although it's obviously a very important part of the platform. It is the graph data, the vertices, the edges that we create and work with. Next is the Nginx, the proxy. Underneath is the REST++ interface, a REST API, graph processing engine, GSQL service, and the visualization, the backend from the Graph Studio. So I mentioned earlier, the GSE, the graph storage engine, is between mapping of external and internal vertex IDs. When you are using the graph database, an application from data model point of view, what you see is vertices and edges with their type, which is a string describing it's a person, it's a company, or in case of an edge, works for, an employee works for a company. So vertices and edges have a type. Vertices have an ID, a unique ID similar to the primary key in the database, and it must be unique. While edges have 2 vertex IDs describing its starting and ending point. And these ending points are described just like in case of vertices as a combination of the vertex type and the vertex ID. Both the vertices and the edges can have properties or attributes. It's actually a property graph. And these attributes either provided as a JSON document or a CSV kind of data structure. But this is only how we end users and applications see the graph. Internally, to save memory, or actually more precisely, to use the memory more efficiently, the vertices are identified by an integer value, a type ID, and a long vertex ID. So these are stored on a lot more compact way than strings. And the same applies to edges. They have a type ID, and they point to the from and to vertex IDs. The attributes of the vertices and the edges are converted in a binary format. The reason I'm mentioning this is that this is what GSE is responsible for. When you are referring to a vertex or an edge, the GSE will have to map these references, human understandable references, to internal storage references, both ways, when you send a query or when the query results are sent back to you. And also, this we'll discuss again later, the GSE determines how the data is partitioned, how it is distributed. Actually, as you know, probably, TigerGraph is an MPP system in a proper production deployment. It is a cluster of nodes working together, providing a fully scalable solution, unlike other solutions when you have to split the data manually. You don't have to worry about it. With TigerGraph, it handles the scalability and the distribution of vertices and edges completely transparent to you. And the GSE determines how this data is actually distributed or how partitioned using a hash function and range partitioning. It's a global service, and it's not really involved in queries themselves. It just does the mapping, and therefore its CPU and memory usage is relatively stable. So this is just a mapping service. The actual action happens at the GP in the graph storage, the graph processing engine. This handles the queries as well as the graph topology updates. When you create new vertices or new edges, it looks after these activities. There could be actually more than one GP instances. In fact, the architecture, as I mentioned, typically consists of multiple nodes in a cluster. And that means that typically there are multiple engines. These graph processing engines store a subgraph, part of the overall graph, and we call that a partition. And within this partition, there might be smaller subgroups called segments. And the segments is actually the unit of computation and storage in the GP. It has the edges, the vertex attributes, and the edge attributes. Let's see how it is relevant for data ingestion. So first step is that we send a query to the system, and so we send the data to the system either from local files in CSV or GSV, JSON format, or as a data stream using Kafka or using the REST API through HTTP posts. There is a dispatcher that takes these updates, queries the IDs, converts the data to internal format, and then send them to one or more corresponding GPs. This is what the GSE does, the storage engine. It does the mapping and the partitioning of the data. And then each GP consumes the partial data updates and processes it and puts it on disk. How does it look like in practice? When you send data in a CSV or JSON format, it goes through the proxy, the Nginx, reaches the REST API. It handles the external vertex IDs to the GSE. It comes back with it returns the internal IDs. And the data with the internal IDs are sent to the Kafka service. It goes into a topic, and all GPs are listening to those topics and then get the data from the appropriate topic partition that belongs to the GP and writes it, synchronizes it to the disk. And when all of the GPs acknowledges the write, then the response is sent back to the application that sent the data. I would like to draw your attention to this word here, observed. As I mentioned earlier, the data in GraphQL, the vertices, have to have a ID, which is a kind of primary key. And this ID, it must be unique, obviously. And this ID is used to store or update the data. It's a kind of observed or merge. The system only stores one copy of each of the vertices. So if you load data twice, the already existing vertices will be retained. Maybe their attributes will be updated, but there will be no duplications. And this is very important to get a consistent result set when you browse data. For example, you don't want to get duplicated or increased number of connections between two people when there is only one connection. Once the data is in the engine, we can start working with this. The user uses the GSQL command line tool, GraphStudio, or the RESTful API from other applications to submit queries using a HTTP GET request. As I mentioned earlier, the GSQL and GraphStudio requests are actually converted into the HTTP request sent to the RESTful API, REST++. The query is parsed based on the graph schema, and it's been forwarded to a dispatcher, which is part of GSE. It queries the ID service, which returns the external IDs to internal format, and it sends it to the graph processing engine. This performs the computation, and dispatcher collects and returns the final GP results to the REST server, and then the combined results are sent to the requester through the HTTP server, REST server in the JSON format. When you create a query, which is our kind of stored procedure, combination of various select and update statements, DMS statements, TigerGraph immediately creates a REST API endpoint for that. So data integration with consumer system is very easy. The system autoconnect provides the interface, and there is no need to develop any middleware. The applications can directly consume the results through this REST API in a JSON format. So this is how request processing actually works. The request is sent through the proxy to the REST API. There is a conversion of external IDs to internal IDs. The query name and the parameters and the translated internal IDs are sent to the graph processing engine, which does its magic. And then when the results are ready, there is a conversion back from internal IDs to external IDs, and the JSON response with these external IDs are sent back to the requesting application. Very easy. Obviously, any enterprise system must provide high availability and scalability. So TigerGraph system comes with a high availability option. As I mentioned, it's a cluster of server machines, and it uses replication to provide continuous service even in case one or more servers are not available or some components fail. The default high availability configuration has a replication factor of 2, meaning that you have 2 copies of each pieces of data, one primary and secondary, stored on separate machines. If one of them goes down, the secondary copy of the data still be available on the other machine. This is default factor 2, but it can be increased. And the high availability cluster needs at least 3 server machines. And here is a example how it works. If you are using the REST PP interface for load balancing, then very simply there are 3 replicas, in this case 3 replicas used to store the data. And if the one of the nodes goes down, you will still have a copy of the data somewhere else. And the data, when the data is written to the system, it uses these internal load balancing to distribute the data. But you can choose to use an external load balancer, which then takes over the responsibility of the HTTP, for the REST PP interface to distribute the data in the replicas. In case of, if the TigerGraph system comes with distributed storage, then the database is partitioned across multiple servers. As I mentioned, the GSE uses a hash algorithms with range partitioning to distribute the data. And the REST PP interface acts as a scheduler and distributor of the data. TigerGraph is ACID compliant, which in this case means that the transactions are not committed until all of the partitions are updated, and we provide strong consistency this way. And obviously, in a production system, you would like to have high availability and distribution. So in that case, you will have multiple replicas and multiple partitions in a system. Talking about ACID compliance. So as I mentioned, Tiger provides full ACID transactions with sequential consistency. Practically, it means that each GSQL query is a transaction. As I mentioned, the GSQL query is effectively our version of stored procedure, a combination of select and DML statements within a query block. All activities belong to one transaction, and it might mean that there are multiple read and write operations within the query, but this is one block of execution, one transaction. And similarly, each REST get, post, and delete operation, which might have actually multiple update operations within it, is a transaction. The ACID compliance, as you probably know, means atomicity, consistency, isolation level, and durability. Atomicity means for us that a transaction with update operations might either delete multiple vertices and edges or update attribute values within multiple edges and vertices. So it's not as atomic as in case of, let's say, an auto commit operation in a data warehouse when one insert is one transaction. It's more like a proper transaction handling in relational databases when you enclose a block of statements within a transaction. And all of the updates and changes within one transaction are all or nothing, either all of them are successful or all of them fails. Consistency means that it's a traditional ACID consistency transaction can include data validation rules. Distributed system sequential consistency in our case means that every replica of the data performs the same operation in the same order. So there cannot be inconsistency. Then it's not possible, as I mentioned here earlier, all of the, oh, sorry, it's earlier than I expected. All of the GPs has to acknowledge the successful synchronization to the disk before the transaction is acknowledged. It's not possible that one GP has different data than others in a distributed replicated system. Isolation level, we provide serializable isolation level. It's the strongest form. It practically means that even if multiple users are working in the system, their transactions or the operations to them seems to be executed as if it was in a sequence, even if other users might have modified the data set they are working on in the meantime. They will not see the modifications until their transaction starts, but I will have a slide on this a bit later. Durability means that all of the transactions are committed, all of the transactions are written to disk SSD or HDD. So data is not lost in case of the system goes down. Let's see some ACID compliance scenarios. The first scenario is when there is a read operation running and the write operation starts a little bit later. The write operation make some changes, but and it might finish before the read operation completes, but the read operation will not see any changes made by the write operation before that's committed. So there are no dirty reads. And even if the write is committed before the read is finished, if the read operation reads the same data of the graph multiple times, it will not see the changes made by the write operation. It's called repeatable reads. And there are no phantom reads either. This is because the graph version, the read operation is working on cannot be changed by any of the write transaction, any of the operations of the write transaction aforementioned. And similarly, if there is a write operation or write transaction running, which modifies the data, the read operation will only see the data that existed at the time it started. So if the write operation hasn't committed the data, that won't be visible. And also effectively, the read operations will have a consistent data set they work on. And finally, if there are two write operations or write transactions, and modifying the same data set, then the second one needs to wait until the first one commits, and then only after that it can start and make the changes and commit its transaction. This is how much I wanted to tell you about the internals of the TigerGraph platform. Any questions at this stage?
Hi, on scenario 3.
Yes.
How do you do anything to work out whether the two writes overlap, or is it just any two writes to the same database?
Because the write to has to wait until the first one starts. My understanding is that there is no how should I say it? There is no check. So we simply, as it's serializable, we put one transaction after the other one.
Okay, so there's no sort of collision detection logic.
I'm not 100% sure. Rick, do you have any information on this?
I believe not. It's nature of distributed databases. It's rather difficult to do collisions across the cluster and consistently. It's essentially a last write wins approach. This is why it does upserting, for example, into keys. We don't check for primary key collisions. We simply overwrite.
Thank you.
Okay. I would like then now to move on to the new features of TigerGraph 3.0. This will be available soon, first as a limited release for our existing customers, power users who would like to compare it to 2.5, which is the current version. And then later this year, obviously, there will be a generic availability, generic release. So let's move to this. The slogan for this version is no code graph analytics for all. And for all might be not relevant for the C-levels, but definitely all kinds of people dealing with data, data analysts, scientists, engineers, people who normally don't write code or don't want to understand all of the intricacies of a complex system should be able to use it easily, because they provide two new features that makes, on one hand, data migration from the relational database is very easy, and the other hand, developing queries on this data. Let's see the details. So the first new main feature is no code migration from relational databases. Effectively, I will show you a video because I don't have the build available that contains this feature. I have an earlier build. So the no-code migration means that you can, through a few clicks, define what database, relational database instance you want to pull the data from, specify a few details on that, and TigerGraph will generate everything to pull that, to be able to pull that data over. Which means that you don't have to write the loader code. We have a very powerful and flexible loader functionality. It has not a very complicated syntax, but definitely visual interface. Using visual interface makes it even easier. I will show you in a few minutes. The second main new feature is no code graph analytics using the Visual Query Builder. The GSQL language is, I believe, a very easy to learn language, especially for those who have some SQL experience. It was very easy for me to pick up it quickly. There are a lot of similarities, very gentle learning curve, but it might not be everyone's talent or interest to write code. And for those people, visually assembling a query in a few minutes or even seconds would be a more appealing way to interact with the database. And there are, of course, all kinds of additional features and improvements. The two main here that will be actually very interesting is, one is user-defined indexing. Currently, in version 2.5, we have the primary key or the ID for the vertices, and it's very easy to look up, very fast actually, to look up vertices using this ID. But if you are filtering or searching using a attribute, currently it's a kind of full table scan. Now the full vertex set needs to be scanned to find the required vertices. And that might be time consuming if you have a lot of data. Using indexes, which are pretty much the same thing as indexes or secondary indexes in a relational database, this will be a lot faster now, making TigerGraph even faster than currently is. And even now we are probably the fastest graph analytical platform. Another interesting feature that will be relevant to the operations team is easier and faster deployment across distributed environments. It will be a lot easier to handle bigger data sets, multiple distributions. I will talk about that a bit later. So let's start with this no-code migration from the RDBMS. Currently, we provide in the first round connectivity to PostgreSQL and MySQL. When you migrate data from the RDBMS, you just pick the source of the database, source of the data, you specify the database connection details, you select tables and attributes to migrate, and then load the data. But let me show you the video here, which explains it all nicely. So it was a very short video, 2 minutes, and effectively it just shows how easy and quick it is to migrate data from a relational database. I have seen it in real life, demonstrated to us a few weeks ago, and practically this is it. You just select your database instance, specify what you want to pull through, and let TigerGraph handle the rest. Yeah, the other great feature, and I will be able to demonstrate this, is no-code graph analytics with Visual Query Builder. As I mentioned earlier, TigerGraph has a language called GSQL, a graph structure query language, which is a SQL-like language, a fully tuning complete language that can be used to query and manipulate graph data. It is, because very similar to SQL, very easy to learn, especially those coming from relational database background. But as I mentioned, some people might not have the affinity to learn a language, or they just don't have the time. So for those people, we provide this query builder, which allows you to visually bring the components of a query together. But it's too much talk. Let me actually jump into a presentation of these. So I have a TigerGraph 3 beta. I doesn't show here, I thought. Running on my computer in a virtual machine. This is GraphStudio. I'm not sure how many of you have seen GraphStudio. This is the primary interface to interact GraphStudio, unless you like to use a command line tool. It has actually two main views. It provides this query, the schema development and query development interface. And it also provides an admin interface that I will show you a bit later. It has a few main functions, primarily to design, first of all, design the schema, to define the vertices, their attributes, the edges between the vertices and their attributes. It's very easy to use. You just create a new vertex, add an attribute, and you click OK, and you get one of these, like person, which has the ID, a kind of primary key, an icon, a color, and the attributes. And similarly, defining a edge is very easy. Just drag a line between one vertex and the other. You give it a name, you specify your attributes and array. So once you have designed the schema, you need to map data to the graph, and it's done in a very easy way. You just specify which data files you would like to use. You can pick its details, format, delimiter, end of line, enclosing sync slider, whether it has a header or not, and that's it. Once you have the data files defined, you just map the content of the data file to a edge or vertex. For example, here we map these two columns, the name and the department the person works in, sorry, the skill the person has, into the ID, sorry, in the source vertex and the target vertex. And the target vertex here, in this case, the skill is populated from another file which has a list of skills mapped as both as ID as name. Once you have the data mapped, you load the data from the sources. And these are the 3 steps that you can actually completely skip if you are using the database migration, the local database migration. Once you have the data loaded, you can start exploring the graph. You can search for, vertex. And then by double clicking it, you can explore its relations. But the real value comes from running queries, doing more complex, deeper analytics, multi-hop, deep link analysis of the graph data. And that required, up to this point, writing queries. I don't have a query here now, but I will show you a bit later how does it look like. It's not complicated. It's, as I said, SQL-like language, but there are some tricks and some skills that you have to write a good, efficient query. This is made a lot easier by building these queries in a visual way. And let me show you a simple sample first. We have this person vertex type, which lists people, and as I showed you here, this vertex can have, this vertex has a name, height, gender, marriage status, and birth year. This first example would like to find people who are under age of 30, which means that I'm looking for people whose birth year subtracted from the current year is less than 30. So how does it look like? Let me show you. So we have selected the person vertex type, and we created a filter, which is, let me assemble it for you. It's easier to show that way. Then move on. So I'm looking for people. Okay, and I want to filter these people by age. So I'm adding a new condition. I want to compare 2 values. And the first value would be an additional expression, a difference between 2 values or two sub-expressions. The first one will be a fixed number, an integer, which is the current year, 2020. By the 2020. By the second one will be an attribute of that vertex, specifically the birth year attribute of the person vertex. And this difference will be then compared to a integer value. As I said, I'm looking for people who are younger than 30 years old. And that's it. Once I have this, I save it. Oops, sorry. There is one thing that I missed. I want to include the details of these people in the output, in the result set. Okay, now I save it, and then I can execute it. There are no errors anymore. And here you go. It shows that there are 2 people who were born before 1990. As I mentioned, the output from the queries are provided as a JSON document. This is what the REST API returns to the various tools. And in case of GraphStudio, it converts this JSON into a nice visual format. It's obviously 2 people right now, so it's not as visual as the second demo. Actually, not the third one. The second demo is a little bit more complicated than the previous one. In this case, we are looking for departments with at least 1 male employee. So we first define a filter on the person vertex type, a simple comparison where the gender is male. That's easy. And then we pick the departments, and more specifically, we pick those people who are male and has a relationship between the department vertex types. Specifically, they work in that. And that's it really. There is nothing else that needs to be done. And there are 2 departments, the Graphlet Engineering and the Woolly Research. And again, the output can be seen as a JSON document and then processed by external applications. The third demo is even more complicated. We are looking for a city which has the most people with programming skills. I need to tell you in advance that this data set covers the Silicon Valley area, so don't be surprised about the output, which I believe will be correct even in real life. So what we do here is that we start with people who are linked to who has relation to a city. They were born in that city. And they have a skill, specifically programming. In case of programming vertex, it's a very simple filtering. We are just comparing. Oh, where is it? It doesn't show up. We're just comparing the ID to the string programming. In case of the city, we should see, ouch. We should see some filters here. Actually, not filters, sorry. We should see aggregations here. So first of all, yes, we named the person, we gave an alias to the person P, and we are counting, we are providing a distinct count on the vertex and edge with the alias, little bit, with an alias of P. So it's practically a simple count, counting all of the relations of P, counting distinct connections of P to the city. And then this count is then ordered by descending order, and we set a limit to 1. And that's it really. If I execute this one, it will return, unsurprisingly, Mountain View, and surely there are a lot of people with programming skills. And to show you something more visually pleasing output, here is another example. We are looking for triangular relationships when somebody manages an employee, and this person, I mean the manager and an employee, are both friends of a third person. And here it's a very simple query in a sense that we just specified 3 instances of the person vertex type and established that there should be 2 friend relationship and 1 managed relationship between these 2. There are no any additional conditions or aggregation. So if I execute this, it should return a more complicated graph, a subgraph. Oh, sorry. Yeah, this is better seen. So we have 2 triangles here. There is one here between Jenny, Tom, and Kevin, and there is another one between or amongst Tom, Emily, and Jenny. The last example that I would like to show you is about finding people who attended a university in the Silicon Valley, or were born in Redwood City, but do not work for Graphlet. So in this case, we specified parameters. I will have to specify the actual values for these parameters when I run the query. So here we filter by university name, here by which is actually used as an ID as well. The same here, we filter by city name, which also used as an ID, and we filter by school, university. Again, this is used as an ID. Sometimes if you have unique values, you don't actually have to create some kind of surrogate key value for ID. You can use, for example, the name of the city or the university as the ID. Typically, it won't work because there could be multiple cities with the same name. So the concept that are used in database when you create a meaningless numerical surrogate key is still applicable here. Sorry. So what we have done here is that we filter the city and find all of the people who are who were born in that, sorry, who were born in that city. Also, we establish a link between people and the school through the attend relationship. And the same here with the university, sorry, the company. A person works at a company. And here comes an interesting part. This is what we called a widget, which is either a union, let me show you, either an intersect of the values provided by the relationships, or a union, or a subtraction. So it's effectively a and or relationship and a subtraction. So here, using this union widget or operator, we combine the data set from city and school. And then from the data set, we remove everyone who are working for a specific company. Well, let me run this for you. It will make it easier to see. So S is school. For school, I will specify a value that I save somewhere here. Let me copy paste it. If I can find this, yes. So San Mateo University. For this one, which is city, let's pick Redwood. Sorry, Redwood City, where actually TigerGraph is headquartered. And for company, let's pick Graphlet. Oh, sorry. If I execute this query, it will return these 3 people who were born, sorry, they were born in Redwood City or attended the San Mateo University, but don't work in the Graphlet company. So this is the Visual Query Builder functionality. I think it's very, very nice to use, very easy to use, even for people who don't have programming skills or interest. Of course, while it's easy to work with this, certain cases requires further development. And even here, this query builder can help you, because you can actually save these query, the Visual Query, as a GCQL query. Here it how it does it look like, but let me save it and go to the query developer part. Leave. I don't want to change that. So the Visual Query has been turned into this GCQL query. And here is what you could see in a query. There are a number of select statements. First, this is used to identify the school. The second query identifies the city. The third one identifies the company. More precisely, this identifies people who attended this school, were born in the city, or doesn't work for this company. And then here we join the two data sets, the city and the school data sets. And then from that data set, we remove those people who are working for the company and just print out the results. This is what generated into JSON. So you can start by visually building the query, and if you need to tune it or you need more complex logic, then you can switch to query development. Let me continue with the other features, other new features of Tigergraph. As I mentioned, user-defined indexes are a very important step to improve its excellent performance even further. When you create or define a vertex, you can specify whether you want to index it or not. Obviously, indexes in Tigergraph work pretty much the same way in relational databases. If you have an index on an attribute, then the lookup or filtering on this attribute very, very fast. But there is a penalty when you update or insert data, because the indexes need to be maintained. So you need to find a good balance between a good number of indexes. You want to accelerate your queries, but you don't want to overburden the system with unnecessary indexes. So it requires a little attention by the system administrators to make sure that the indexes are more beneficial than burden. Here is a syntax, but I think we can skip this for now. There is another very important enhancement. It's called schema flexible querying. Currently in version 2.5, if you write a query, you have to specify hard code in the query body, which vertex types and edge types you want to work with. And if you want to port your query or your algorithm to another system, currently you might need to rewrite the query to use different vertex and edge names. This will now be fixed by providing type parameters in query. So you can say that I want to work with a X type of vertex, which might be in some cases a web page, or in some other cases it might be a person. For example, Google's PageRank algorithm typically works on, well, typically it was designed to work on web pages to find out how relevant of web pages by counting the connections or references to that page. But the PageRank algorithm is very generic, can be used very generically in other cases, in even social network analysis or for example, network optimization, to find out, in case of network optimization, which other system would be impacted, which is the crucial component in the system that would impact a lot of additional components in the network if it goes down. So by using this type of syntax, when you can specify the type of the vertex or edge, you can make the queries generic and easily portable to any kind of graph environments. So you don't have to rewrite them, you just specify new vertex types and edge types. This makes very easy to develop universal libraries of graph algorithms. And we have, if you have a look at our GitHub repository, we have already a great number of very sophisticated graph algorithms implemented. Additional enhancements, there are more built-in vertex icons, and then users can upload their own vertex icons, so you can decorate your graph in more ways. And there is something called interpreted query support. I need to provide a little explanation here. Originally, when you created a query, you had to compile it, which meant that the GSQL query text was compiled into C++ code, and then that was compiled into machine code. And then based on that machine code, which was deployed in the database, a REST API was created. And this is very, very powerful in an operational system because this guarantees the fastest possible query execution and immediately provides integration point for downstream consuming applications. But if you are a data scientist and you are just exploring the data set, data discovery, you don't want to wait, I don't know, 30 seconds, sometimes a minute, until the code is compiled, the query code is compiled and deployed and the REST interface is created. You just want to give it a try. Let's see what happens. And in that case, to help that case is introduced interpreted mode, in which you don't have to compile anything. You just execute the query in an interpreted mode on the fly. Obviously, it has some performance penalties because interpreted code is never as fast as compiled code. But data scientists, data engineers can save a lot of time during the data discovery phase. Now, this functionality wasn't previously available through the GraphStudio interface. Now you can just simply run the query from GraphStudio without compiling and deploying it first. And as you could see, secondary index was supported. I can just click a checkbox to say that I want an index, a secondary index, an attribute, and this is also supported in query execution. Very quickly, I would like to show you the two enhancements in the admin console. As I mentioned, the GraphStudio actually has two interfaces, the actual GraphStudio where you develop your schema and queries, and the other interface or other view is the admin view. It provides a dashboard, which was available previously. You can monitor the system components. And now we have a user management page where you can do what you would expect, manage users, roles, and things like that. And now we have a detailed information about the license, what it gives you access to, or what it allows you to do. And now by clicking this file, you can upload a new license to renew the license. System management, there is an important development here, pardon for the pun. The export-import utility. Obviously, you could always backup and restore the database, but that was a kind of physical backup to make sure that you have a safety copy of your database. Import-export acts as a logical backup. It's a complement to the backup restore, not a replacement. The main purpose is to move database instances easily, so you could export your database instance from, let's say, a development instance and deploy it into a production system or another development environment. And you will be able to, this is two GSQL statements, export and import, very creatively, innovatively. You can export everything, all the components, including the data, or you can just export the schema or the data or the users or a template with everything without the data. And it creates a zip file that you can then even encrypt and send it over to someone who can then import it into another database instance. And I mentioned earlier that we have a new installer, which runs in parallel to improve installation time, although I think it deploys very fast anyhow. and it allows users to maintain more than one set of binaries to be installed. So for those who are reluctant to jump into a new version immediately, they can deploy the new version in parallel to the old one, and gradually confirm that it works still as expected, and then migrate at a later stage. And that's it. That's all I had to say tonight. And I would be happy now to answer any questions you might have regarding either the architecture or the 3.0 new features. Were there any questions during the?
We had the question. We had one of the questions which you answered already. I don't know if anybody else has any. Also, Andrew asked whether we would be sharing the slides, which we will be doing, and also I'll share the recording as well. We'll get that. We'll get a link to that over to you.
Yes, yes.
Well, thank you, Szilárd.
You're very welcome, and thank you for everyone who attended this presentation.
Thanks, everyone, and if there are no more questions, I guess we can draw this to a close. And thanks very much for attending.
Yeah, and if anybody wants to get in touch with us, then you know where we are.
Yeah.
Thank you. Thanks, guys.
Thanks,
Okay.
everyone.
Have a
Have a
good
good evening. Thank you.
Stay safe.
Bye-bye.
Stay
Stay
healthy.
safe. Yeah.
Thank you.